versus physically. So this talk is based on several papers. This is collaborated with various combinations of these collaborators, and I would also like to recommend to you this very wonderful compact review by Dracus and his collaborators. So they reviewed almost every aspect of Wilson loops in three-dimensional Chern-Simons method series. Okay, now I would like to briefly review Wilson loops in general gauge theory and also in ADS-CFT correspondence. We all know that Wilson loops are very important non-local observables in gauge series. Wilson introduced these non-local operators because I think his main motivation at that time is that the vacuum interpretation value of Wilson loops can be used as a criterion for quark conformant or more generally color conformant. Wilson loops are also related to other very important quantities in gauge theory. For example, cusp anomalous dimensions. They also appear in infinite divergence of scattering amplitude. Wilson loops is also related to Brahms-Handel functions, and in spatial theory, like four-dimensional equal to 4 Super-Chern-Simons theory, that's like a polygon Wilson loops is closely related to scattering amplitude of gluon in the Planar limit. In super-symmetric gauge theory, we usually need to some modification to Wilson loops such as this new operator will preserve some part of the supersymmetries. In this formula, if we drop out the part including scalars, then this is the usual definition of Wilson loops. In four-dimensional equal to 4 Super-Chern-Simons theory, but China included the coupling to these 6 scalars in the adjoint representation of the gauge group. In special cases, this Wilson loop will preserve half of the supercharges. For example, when we weaken rotating to Euclidean space, when such a Wilson loop is a line or a circle, when this parameter yi satisfies certain conditions, this Wilson line or Wilson loop is half BPS. In the ADS-CFT, yes, so but here introduce this new loop operator in the framework of his ADS-CFT correspondence. The most studied example of ADS-CFT correspondence is the correspondence between four-dimensional and 4 Super-Chern-Simons theory and type 2B string theory on the background ADS-5 times S5. We all know that the gauge theory in the large N and the large to the coupling limit is due to weakly coupled classical supergravity or weakly coupled classical string theory. So to study this half-place Wilson loop using ADS-CFT correspondence, we need to first give a graphical description. When this Wilson loop is in fundamental representation, the string deal is just a fundamental string in ADS5. And the worksheet of this fundamental string has a boundary along this circle. The circle is just the one to define this Wilson loop. The classical equation of motion of a fundamental string theory tells us the worksheet should be a minimal surface inside ADS5. This gravity dual is directly related to semi-classical string solution in ADS space. So you can compare this with the theory for endpoint functions. In that case, in fact, you need to use classical supergravity solution. So in this sense, for Wilson loop, this gravity dual is more stringent. When the half-previous Wilson loops are in high-dimensional representation, the gravity dual could be deepened or a new supergravity solutions. Let's go back to half-previous circular Wilson loops in the fundamental representation. For this case, based on some participative calculation, these three authors conjectured the computation of the wave can be reduced to a simple computation in a Gaussian metric model. This conjecture was soon supported by the study of conformal anomaly. If you accepted this conjecture, then you can obtain the result from the metric model and take the large n and the large copy limit. The result is like this. Then you forget about this p-factor. This expression part is just exactly consistent with the result from the string theory dual. I think this is the first very non-trivial check of ADS-CFT correspondence beyond non-renormalization theorems. Later, the reduction to Gaussian metric model was proved by Patrick using his supersymmetric localization. There are many other important results in four-dimensional case, but today's focus is on three-dimensional case. 1 year, just 1 year before ABGM theory, Gato and Yin constructed half-previous Wilson loops in three-dimensional equal-2 Super-Chern-Simons theory. You can see this construction is very similar to the four-dimensional construction. Later on, just starting in this year, the study of Super-Chern-Simons theory is largely inspired by the study of multi-membranes in 11-dimensional M theory. So first, Barger, Lambda, and independently Gustafsson constructed the three-dimensional n equal to 8 theory based on three algebra. Very soon, it was read that this theory can be rewritten as a Chern-Simons method theory. You can choose not to use this three algebra language. This inspired many important works and a great achievement is obtained by Ahnoni and his collaborators. They first constructed three-dimensional equal to 6 Chern-Simons method theory and started from beam construction. They give very strong evidence that this theory is just the low-energy effective theory for multi-M2 beams on C4 or decay orbifold singularity. Then you take the near Horizon limit of these black membrane solutions, you will know that this theory is due to M theory on ADS4 times S7 over decay, or type 2A string theory on ADS4 times CP3 when you take the large K limit. ABDM theory is a Super-Chern-Simons theory. The gauge group is UN times UN and the Chern-Simons levels are K and mass K. The matter field includes 4 scanners and 4 fermions in the bi-fundamental representation. Soon after this theory was constructed, 3 groups, including myself and Professor Bintin, studied simple BPS Wilson loops in this theory. You can see this construction is another way of gas and in. But very surprisingly to us, if you use this kind of construction, at the most you can only obtain 1/6 BPS. This is surprise because in the string theory or M theory side, we have very good candidate of fundamental string solution or membrane solution to deal to Wilson loops. And you can find this solution are half BPS. That's tell us there should be half BPS Wilson loops in the physics side, but among this construction, we couldn't find them. This becomes a puzzle. This puzzle was solved 1 year later by Drucker and Transcendini. They constructed this new type of Wilson lines. One of the important points is that you should include fermions in this construction. Another key point which was better understood by other authors is that for the Wilson line to be BPS is not necessary to demand the supersymmetry transformation of this connection L to be BPS. It's enough to demand the supersymmetry transformation of the connection can be written as a covariant derivative in L itself as a connection. This construction was expanded by EPH mechanism by Kim Ni and Sanjay Ni. They also obtained 2/5 BPS Fermionic Wilson loops in equal to 5 series. Then I want to see whether we can construct such a fermionic Wlison loops in series with less supersymmetry. The first result is we obtain such a Wlison loops in case. At that time, we thought that maybe this is the end of the story. But partially inspired by the observed we obtained some new construction in equal case. So you just begin with the very general quiver theory. You pick out the two adjacent nodes in the quiver diagram. You write down you consider some answers for each Wlison loops and solve the previous condition. Sorry, there are some problem here. Sorry. A moment. Okay.
We can see it. We can see it now. Yes. Can you try switching slides? Yeah. Very good. Yeah. It seems to be working now, Junbao. Yeah. Thanks.
Okay.
Thank you.
Thanks. And I need to be quick. Okay. Let's continue. So you begin with this general construction, and you try to solve the previous BPS conditions. We find the forecast of the solution to the BPS condition. Previously, we thought we obtained the forecast of BPS for Fermionic Wlison loops. But later it was pointed out to us by Docker that the last two classes were due to some trivial Wlison loops. So the only the first two classes are useful. Then we use this construction in equal to 2 series to back to AVGM series. We find some new non-trivial Fermionic 1/6 BPS Wlison loops, and the interpolate between Platonic 1/6 BPS Wlison loops found by Gato and found by the three groups and from Fermionic half BPS Wlson loops by Docker and Trandini. And these new Fermionic BPS Wlson loops obtained some further studies. Korea and collaborators suggested about the gravity dual of this new Wlson loops. They found that we need to use a very special mixed boundary condition on the watershed of the fundamental strings. And these Wlson loops can be understood as a marginal deformation of half BPS Wlson loops. This point of view was also supported by recent classification of super-conformal line defects. But this point of view is very hard to prove. I mean, it's very hard to prove that this deformation is marginal at the quantum level in the physics side. I skip this too. So in the above construction, only two adjacent nodes in the quiver diagram are used. And these around 4 years ago, the median group constructed Wlson loops all of such classes in the equal to 4 or before the every given series. Sorry, this sentence was deleted. And very importantly, some of their Wilson loops has a very clear gravity field. Then myself and Oyan joined them to generate this construction to generate angle 2 quiver Simons better series. So we go back to this quiver diagram and we go back to this general quiver diagram. Then we consider more general answers for the Wilson loops, and in this case, all of the fields will be used. Then we still we try to solve the BPS conditions and find these solutions. So this is much general than what we obtained before. There are some, sorry, what's wrong? Yeah, there are some interesting features of this new loops. First, the diagonal bulk of the connection should always be botanic for them to be BPS. Second, if A and B are different nodes in the quiver diagram, then you consider the off-diagonal bulk. You find in some cases in this bulk called small AB, the botanic part and the fermionic part can be non-zero at the same time. But this can only appear when there are triangles in the quiver diagram. Because of these conditions, so this does not appear before in AVGM or before the equal to 4 or before the AVGM cases. We obtained a very important byproduct during these general constructions. We obtained some half BPS Wilson loops in angle 2 quiver, angle 2 orbit AVGM series, and this Wilson loops has a very clear adversary drill. We obtained this precise duality based on some orbital body. I think this byproduct has very important implication for more general cases. So long time ago, Facquet and Sparks studied the duality between bosonic Wilson loops and some simple problem BPS brain solutions. And at that time, they give some strong evidence for the duality they suggested. The evidence mainly includes the matching of preserved supercharges and the web of Wilson loops from localization is consistent with the results from the spinary or adversary drill. But now, because of based on our results in equal to 2 or before the AVGM series, I believe that the previous duality should be modified. I believe that that duality is not true in previous form. The reason is that based on the results in angle 2 orbifold series, I think the Wlison loop due to simple proper membrane solution should be fermionic instead of bosonic, because at that time in 2013 in angle 2 series, there are only bosonic Wlison loops. So the fermionic Wlison loops in this series with less supersymmetry was constructed by us 2 years later. Then you may ask why their strong evidence is not enough. The reason is that first, classically, some bosonic and fermionic BPS Wlison loops share the same supersymmetries. If this is still true at the quantum level, if there are no some related anomalies, then these bosonic and fermionic Wlison loops share the same supersymmetries at the quantum level. Then you cannot use supersymmetry to distinguish them. Then you cannot simply use supersymmetry to justify which one is due to the simple BPS membrane solution. This is the first point. Secondly, if there are no such related anomalies, for given fermionic BPS Wlison loops, there are bosonic ones in the 7Q cohomology class, and this Q is just the supercharge used in supersymmetric localization. So, under the assumption there are no related anomalies, these bosonic Wlison loops and the fermionic BPS Wlison loops has the same waves. So you cannot use the waves of them to justify, to distinguish them, to know which one is due to the membrane solution. So I want to convince you that in the angle 2 or 3 Super-Chern-Simons meta series, the precise map between BPS Wlison loops and the BPS proper membrane or string solutions is still unsolved question. The pre-Wilson proposals, that bosonic BPS Wlison loop is due to simple membrane solution is very likely to be wrong. We should consider fermionic BPS. Sorry. We should consider fermionic BPS Wlison loops and to see which one is due to certain proper BPS membrane solutions. Finally, I want to finally I want to go back to the problem of this would be anomalous. So the question is that some fermionic Wlison loops and bosonic Wlison loops share the same supercharges at the classical level, but we don't know whether all of these fermionic BPS Wlison loops are truly BPS at the quantum level. Maybe there are some conditions like anomalies here, but we don't know. Recently, results from the statistical side or from the classification side indicated there are no such anomalies. But it's very hard to prove this in the field service side. Maybe I just stop here. Thank you very much for your attention.
Thank you very much, Junbao. Thanks. Are there questions for Junbao? We have, in principle, plenty of time. I have a couple of questions while other people may be coming up with further questions. Junbao, perhaps coming back to this issue of the further questions that you were mentioning. So my understanding is that you have given some representation theory arguments for why the bosonic Wilson loops may give rise to the same quantities as the fermionic ones, because they belong to the same cohomology class and they will share the same vacuum expectation values. But did I understand correctly that what you are saying is that it's hard to find a quantity where the bosonic and the fermionic Wilson loop give rise to different answers while being computable with the techniques that we have? Is this what you are trying to say, or did I miss the comment about the Konishi anomaly?
There are two points here. First, if we accept this assumption, there are no such conditional anomalies, then till now, I didn't find a quantity to distinguish them.
Right.
Maybe we need to consider some coordination functions of this Wilson loops. But the point with local operator, but the point is that if there are no such anomalies, if you want to use supersymmetry localization to do some non-perturbative calculation, then you cannot find, it's very hard to find a quantity to distinguish them. Maybe, of course, from the results in the gradient side, maybe there are no such a coincident anomaly, but it's very hard to prove such an anomaly that exists. So maybe the better way to build this precise map to try to consider some randomization for now between toric theory and orbifold theory. Maybe consider some toric 7-dimensional Sasaki as a manifold. So let me go back here. So in this case, this 7-dimensional manifold is Sasaki answer. Maybe we can try to consider some toric Sasaki and toric case and study the RG running between toric case and orbifold case. Then you try to carry the results from the orbifold case to the toric case. But this is the future idea.
Yeah. No. Okay. So what you are saying is that indeed it is technically very challenging to find something that is computable that may be able to distinguish between the two objects. And then I had a second question. This is because of my ignorance, so apologies for that. But when you were reviewing how to study the supersymmetry of these Wilson loops, even though it was very clear, I just wanted to know whether exactly, this is actually the slide. So is the mathematical problem of identifying all possible supersymmetric Wilson loops, has this been classified mathematically? So if I give you a capital L as what it's appearing in the at the bottom of this slide, is there a mathematical result classifying every single L, or is there any room for some extra work here?
I think there very little room, but I think the mathematical classification is hard.
Okay.
In some simple case, you can do some small classification. In one of my papers with Hall and Jiaju, we do some. I don't know. It's very hard. So we just excluded some. We just excluded the case when the theory is in Minkowski theory and the water line is space-like. That can be excluded. But for other results of classification, I think it's not easy.
I see.
Because okay. It's not easy to in some cases, you want to prove such an equation has no solution.
Solution, okay.
Yeah. I think it's not easy.
No, I appreciate it's not easy. I think that the reason I was asking is because, for instance, when you ask similar questions on supergravity, for instance, you have this killing equations or generalized killing equations, and people can come up with some kind of general results about the existence or non-existence of BPS configuration. So I was wondering whether there is a similar kind of a statement for Wilson loops, but yeah. Are there further questions?
Sorry. Just one comment.
Yeah.
So in the bosonic case, in four-dimensional case, there are some partial classification by Preston, but it's not complete. You find in four-dimensional bosonic case, you find the BPS condition is closely related to the pure spinor condition.
Right.
But for the case beyond the pure spinor, there are still some BPS Wlison loops. That result is very interesting.
No, that's a useful comment. Of course, I had forgotten that there is the issue between bosonic and fermionic Wilson loops indeed. So for bosonic ones, there are some results. No, thanks. Thanks. Are there questions for Junbao, either in the chat or in real time? I don't see anything in the chat. So if there are no further questions, let's thank Junbao again. Thanks.
Okay.
Nice and interesting talk. Thank you, Junbao.